So did you get my email on homework? Right, so the first set of homework, including like 3 different assignments on that, it's just like a quick review for you. A lot of you have done this type of materials before, so just you have about like 10 days to complete the assignment. Hopefully it should be good, but if you have any question, again, email me. So let me try to finish lecture 2 first, and then we're gonna switch to LaTeX project, which is the first project. So in lecture 2, we went over the definitions of scalar vectors and the properties of vectors, as well as the dot product and properties of dot product. One of the application of the dot product is projections, right? So for projections, assume that you have 2 vectors with the same initial point. In this case, you have vector u and vector u here and vector v. Projections is that you want to project a vector v onto vector u. When you do that, you have 2 things happening. Right? You have a shadow, right? It's just like the sun. It's got a shadow on the ground. Similar to this, the projections of v onto u give you a shadow. That shadow is vector. And you can have the measuring tape and measure the length of that shadow. And the length of the shadow is called the scalar projections. Okay. Yes. Okay. So we derived the formula for this scalar projections last time using the information outside of the angle between the 2 vectors. Okay. And as well as the formula of the product. So this is what we derived last time. Okay. And that is the scalar projections. For the vector projections has the same direction as the vector u, right? So therefore, to show that in the vector projections, so the vector projection of v onto u has the same directions as vector u, then you have the formula that the projections vector projections of v onto u is equal to, now whatever the length you have here, which is the scalar projections, you multiply with the unit vector of vector u, right? So this you are taking from the scalar projections. And then you use a regular multiplication and multiply that with the unit vector of vector u. So the vector projections has 2 components here, right? The first component in the parentheses here is the length of the shadow. And the second component to indicate that is you need to follow the directions of vector u. Okay, so that's the vector projections. Okay. So you have different situations. One situations for the vector projections is u and v pointing in the right directions. On the second graph, you have u and v pointing in the left directions or directions to the left. It means the same thing because you just want to find the projections of v onto u. So this is still the projections of v onto u. And again, in this case, you have the red part, which is the length of the projections. So this one is x, or the component of v onto u. That is again the scalar. Okay, any questions on this? Yes. This one? Theta. So this one is theta. So if you haven't been able to capture on the notes on the board here, again, I have videos, so you can go back and review or watch that if you want to. Okay. So any questions on projections? We good? All right, so I'm going to move on to another application of the dot product, which is the work done. So by definitions, the work done is the total amount of effort required to move one object from one position to another positions. So I'm gonna use this table to demonstrate the concept, right? So I want to move this table from this position to this. Pull or push it. So that's I apply a force to move the table from one position to another position, and I get the work done. Okay. So the work done, usually denoted as capital W, is equal to the force multiplied with distance. Right, the cross in the formula is the regular multiplications. And this formula is, so the formula outlines only when the force is directed along the line of motion. And when I say this, I assume that the line of motion is the horizontal and not vertical directions. So mainly I have three different scenarios here, right? And all of these three example, I assume that the line of motion is in the horizontal directions. So this is the distance, right? Moving in to the right. In this case, also moving to the right, this case, the line of motion. Now, in the first case, I apply the force vertically or perpendicular to the line of motion. Okay. So in this case, I apply F, and obviously because we want to move the object to the right or in the horizontal directions, when you apply the force vertically, there's no work done in moving the object from one position to another position horizontally. You're okay with that? So in this case, work done is equal to 0. Now, in the second case, I'm pushing the object, right? So I'm right here, this is my object. I'm pushing it in the horizontal directions, right? Because I'm going with the line of motions, therefore the work done here is going to be positive. You okay with that? Again, I want to move this table from this position to my right. Okay? But because look at the example, I'm actually pulling to the left. Therefore, the work done now is negative. But in reality, we don't usually have this nice situations, okay? When you move a table by yourself, just pushing, right, or pulling horizontally, what do? You carry like this. And that. So that is more realistic situations. Now, suppose F is pointing in the directions different than the line of motions. Right, or horizontal directions. So what you want to do is you want to calculate the amount of work done contributed to pulling the objects in the horizontal directions. Okay, so this is the way I applied the force. So usually as an angle like this. So D, this is D, this is the line of motion. This is the force that I'm going to apply onto the object. Okay. So by doing this, by pulling the object with at an angle like this, so you point, you have the force and the line of motion form an angle, and that angle is theta. Now, when you apply the force at an angle like this, right, and you want to pull it in the horizontal directions, there's only part of the force get applied or get contributed to moving the object to the right, okay, or in the horizontal. And at the same time, you kind of waste the work done or some energy in the vertical direction. You with me on that? Okay. So here, you project this onto the line of motion D, right? And you have this part, I call this part X. Let me use another color here. So first let theta be the angle between F and D. So you have angle, you have what you want to know is like how much the force get contributes to in moving the object to the horizontal direction along the horizontal directions. So you're looking for X, right? So you use cosine formula. So cosine of theta is the adjacent over the hypotenuse. the hypotenuse here is the length or the magnitude of the force. Therefore, in this case, you have x equal to the magnitude of F multiplied with cosine of theta. Now, what is the work done? The work done is what? Force times distance. Okay. And now the force in this case is not fully F, right? It's a part of it. It's just X, because X is the amount that gets contributed in moving the object in the horizontal directions. So therefore, the work done is equal to the magnitude of F times cosine of theta and multiply with the distance. If you rearrange the formula, you let work done equal to capital W. You get that F, the magnitude of F times the magnitude of D times cosine of theta. And this is equal to the dot product of F and D, or F dot with D. So this is another application of dot product in calculating the work done in moving an object from one position to another position. And this is true for all the cases that we have so far, including the vertical force, the force going with the directions, and the force go against the directions. Okay, and we covered this kind of relationship last time, right? If F and D are perpendicular or orthogonal, then product is equal to 0. So work done. If F go along with D, the same direction as D, then this is going to be positive, right? If F is against D, so dot product is negative. And if F is line with applied at an angle compared to D, then all right. Any questions? Yes. Physics? Yes. Yeah. So we going to revisit this particular topic in a few weeks when we calculate something the line integral of the vector field. This is the perfect scenario. There's no error system. So if you move the object outside with the wind, what's going to happen? So that is the line integral of the vector field. All right, so that's the application, another application for the dot product. So that's it for me for lecture 2. Now let's switch off to project 1. Any questions on lecture 2? Yes. This one? Okay.